excellent. Okay. We also learned that other ionic compounds are insoluble. What does our data booklet say instead of insoluble? Low solubility. And it's important to remember that not only will such a compound not dissolve if you throw it into water. So for an example, if you have a piece of chalk and you throw it into water, it will not dissolve. It'll just sit there. But in addition to not dissolving, yes? Yes, in addition, it will form a precipitate. So if I take, say, some silver ions, so let's say I had a solution that contained silver ions, and let's say I had another solution that contained chloride ions. If I mix them together, those insoluble salts will form a precipitate. Okay? Could I get a solution with just silver ions in it? No, they would have to come with a partner. What would be a good partner for silver to make a solution of including silver ions? Pardon me? NO3, because NO3 nitrate is soluble with everything. How about chloride? Who would be a good partner for chloride? Sodium. All right, and then we would have our AgCl solid precipitate. Okay. So as you said in the video, this is an oversimplification. Having no ions at all is not how it really is. Even insoluble compounds will dissolve to a teeny tiny little bitty degree. Okay? This is why your solubility table doesn't actually use the term insoluble, it uses the term low solubility instead. So you can see up here, if we were to just write concentration and not give it a unit or anything, we'd say this has a concentration of 4. Yes, there's 4 particles per whatever volume that is. Okay? I know that's a silly sort of a concentration, but we're just going to go with that. Can we do that? Okay. There's a reason for this. We're going to have another one later on. The degree to which a substance dissolved can be communicated by its solubility product constant, which is also known as the KSP. And KSP is just a KEQ for a solubility equilibrium. So just like any other equilibrium, it is a dynamic process with a forward reaction and a reverse reaction. In this particular case, the forward reaction will be that some of the ions will dissolve out of the crystal. But at the same time, these two are taking place at the same time. I just thought it got too messy if we drew it all in one. At the same time, you have other ions which are rejoining that lattice, that crystal lattice. Yeah? This would be our reverse reaction. Overall, though, after we've had a couple particles dissolve and a couple particles recrystallize, the overall concentration has stayed the same, right? Because the concentration down here is 4. We have 4 particles. 1, 2, 3, 4. Just like up above, we had a concentration of 1, 2, 3, 4. Yes? What kind of a property is concentration? Yes, it is a macroscopic property. And what do we know about macroscopic properties at equilibrium? They do not change. Okay? Macroscopic properties do not change at equilibrium. So that's why our concentration remains constant. And it remains constant because the rate of dissolving equals the rate of recrystallization. The forward rate equals the reverse rate. And this brings us to, because we have an equilibrium, we can write our equilibrium constant, which in this case is called the KSP. But in order to write any equilibrium constant, you need to have a reaction, yes? When we did this in the equilibrium section, there's so many different possible reactions that you weren't expected to write them down. But for this one, you will be expected to write this. This is called the solubility equilibrium equation. Also known as the dissociation equilibrium equation. And you will be expected to write this anytime you use something where you're finding a KSP, okay? So you'll be given something like AgCl, and you'll be expected to be able to write the solubility equilibrium equation. And one thing you're going to notice about this, where is our solid? Is it in the reactants or is it in the products? It's in the reactants. The solid, when we write the solubility equilibrium equation, will always be in the reactants. It will always be on the left. Have we always written our solid on the left when we're dealing with low solubility salts? What about those double replacement reactions that you've been practicing, or at least I hope you've been practicing? Where did the solid go in those ones? It went on the right, and just because I did it with my morning block because they weren't quite sure where it went, but I think it's good practice anyway. I'm going to have you guys practice writing the net ionic equation. If you need extra paper for this, that's fine. Okay, I've got actually lots of scrap paper. Equation for the reaction of FeCl3 and SrOH2. If you are able to go straight to the net ionic equation, you are welcome to do so. But many of you will still prefer at this point to go through the whole, let's write our formula equation, complete ionic equation, and net ionic equation. You need two things for this. You need a data booklet. Is there anyone who needs a data booklet? And you will need some paper because there's probably not enough room on your worksheet there. Does anyone need some blank paper? Okay, so give that one a go. It's good review for your quiz on Tuesday. If you're at all getting stuck, you can write out your reactants. And these will be aqueous. Sorry, I should have mentioned that. And once you've got that, you can write the ions. And you can use those ions to help you figure out what the products will be. Now, it's totally fine if you went straight to the formula. Yeah. If anyone's having any challenges, don't forget you combine your outside ions and your inside ions. So we'll have FeOH3 and SrCl2. And we look up those solubilities. Is iron hydroxide solid or aqueous? Solid. Strontium chloride is aqueous. Now, can I just go splitting apart my ions yet? No, what do I have to do first? Yes, balance. And if you have 2s and 3s, you can remember that the easiest thing to do when you have 2s and 3s is to find the lowest common multiple, which is 6. And so you can say, I have 3 chlorides here, 2 chlorides here, so let's put a 3 in front of this one and a 2 in front of that one to give me 6. Did I do that the wrong way? I did that the wrong way around. I have 9 and 4. That's not going to work. So we'll put a 2 in front of this to give us 6, and a 3 here to give us 6. Thank you. I noticed those looks, all those like consternation. What are you doing, Ms. Spence? You crazy lady. And again, with the hydroxide, we have a 2 and a 3. Let's see if I can do it right this time. We need a 3 there and a 2 there. When you go to split everything apart, you need to take into consideration both the coefficients and the subscripts. So I'm just going to quickly rewrite this down here, FeCl3, because it's too messy otherwise. Or actually, maybe I could just get rid of this. Look at that. Oh, so nice. Okay, good. That's done. So now I'm going to split things up. How many iron do we end up with? 2. How many chlorides? 6. How many strontium? 3. How many hydroxides? 6. And all of those things are aqueous. How many irons? Trick question, it's a solid, so I don't take it apart. There are 2 ions, but I don't want to split it up. So we have 2 FeOH3 solid. And now I'm running out of room, so I'm going to make my screen small or bigger. There we go. How many strontiums? 3. And how many chlorides? 6. I feel like you guys have a better grasp on this than my morning block did, but maybe I'm wrong. Maybe you're just not talking to me. That's okay. Anyway, that looks good. What do we do? What format is this? What equation is this called? This is our complete ionic equation. What if we want our net ionic equation? What do we need to do? Get rid of our spectator ions. Who are the spectators? Can you imagine if you tried to have a conversation with somebody and they never answered you back? Would that not be like the weirdest, most awkward thing ever? I put up with it every day. It is the weirdest, most awkward thing ever. Yeah, we got strontium and chloride. Thank you so much. I appreciate it. And you guys have been doing a great job already, so thank you very much. Okay, strontium and chloride. Get rid of those, and we have our net ionic equation. 2Fe, 3 plus, aqueous, plus 6OH minus, aqueous, gives us 2FeOH3 solid. Are we done? I picked this as an example on purpose. Yeah, we have to reduce, okay? We need to go to simplest terms. All the coefficients are divisible by 2. So reduce to lowest terms. And so what we will finally end up with is Fe 3 plus 3 OH minus goes to Fe OH 3. If you're getting good at this whole process, and you don't need like tons of practice on it anymore, you might choose to say, when I'm not being asked to do this whole thing, maybe I would like to just go straight to my net ionic equation. If you are not already able to do that and you would like to do that, you go through the same process where you say, what are my ions? I have iron, chloride, strontium, and hydroxide. When I combine those two, I ask myself, is that soluble or low solubility? Iron hydroxide is low solubility. Strontium and chloride is soluble. So all you need to do is identify for yourself, what is my low solubility product, or products if there were 2 of them. And you write that as your product. So you would say, okay, my product that is low solubility is going to be Fe OH 3 solid. And now you just say, what do I need to make that? What ions do I need? I need Fe and OH. And you need to remember your charges. And you need to remember it still needs to be aqueous. And it still needs to be balanced. But if you feel like you've gotten enough practice on like the whole shebang, you can make this process a lot quicker if you are just asked for the net ionic equation. On your quiz, you will either be asked for, please give me the formula, equation, complete ionic equation, and net ionic equation, or I will say, write me the net ionic equation, in which case you are welcome to do the whole process, but you don't have to. Yes? Okay. Now, one thing you're going to notice about this, how does this differ from the solubility equilibria equations that we saw over here? Yes, the solid is on the right. So if you are writing a precipitation reaction, you are going to put the solid on the right. Because the precipitate is the product of a precipitation reaction, so it has to go in the products. I'm going to rewrite the other one over here because that makes it easier to see. What else is different between this one and this one, other than the fact that they're different compounds, obviously? This one has a solid on the left, this one has a solid on the right. Yes? One is at equilibrium, another is one direction. When we're writing a precipitation, we are assuming we don't care that it's going to precipitate and then actually start forming a little bit of an equilibrium. We mostly care about the fact that it has made a solid, and we're not going to go past that point. Yes? So we just write it as a one-way arrow. If we then want to look at the solubility equilibrium later, we will then write a separate equation the other way around. Okay? So, now, why are we putting the solid on the left for our solubility equilibrium? Why not put it on the right, and then it would always be on the right and we wouldn't have to worry so much? Well, it's because the math of the KSP makes it really easy. First of all, I guess we should mention that we do not include our solids, but hopefully that's just review from last unit. Yes, don't include the solid. So there's no solid in the KSP. Don't forget your ion charges in there. But by convention, they decided that in the solubility equilibrium, we would always write the solid on the left because it makes for a much tidier KSP expression. So if we have the one on the left here, you can see KSP is just equal to the ion times the ion. So if you're doing math around that, you're just multiplying. Yes? Pretty straightforward. Whereas if you do it like on the right, where you put the solid on the right, now we don't have anything in the product, so we have to put a 1 on top, and then we've got our ion products in the basement. It just makes the math a little tiny bit more complicated, right? It doesn't look quite as tidy. It's not quite as easy. So by convention, they said, let's make them all go the same way. So when we have KSP values, we can actually compare them with one another. If you actually look on page 5 of your data booklet, you will see a whole bunch of KSP values. Yes? So we wouldn't be able to compare them in this way if half the time we were putting the solid on the left and half the time we put the solid on the right. It would just be a problem. But we can compare them if we always do it the same way. And now that we've talked about it, here's the official, an interlude, solubility equilibrium equation versus precipitation. In solubility equilibrium, the solid goes on the left, and we use an equilibrium arrow. But if we write a precipitation reaction, the product is the precipitate, and so the solid goes on the right. And for these ones, because we're not really concerned about what happens after there has been a precipitation, we just use a one-way arrow. There will be situations later on where it's like, okay, we dump these two solutions together, a precipitate forms, and now we want to find the, now we want to look at the solubility equilibrium. And if that was the case, you would actually write the equation both ways. You would say, okay, first, precipitation occurs, right? So we have our solid on the right, and then an equilibrium is established and we have the solid on the left. So you would actually do both. I know it seems like a bit of a pain, but there we are. It doesn't occur very often. Always be sure to put the equation in the right direction depending on the circumstances. I'll let you know right now, the quiz coming up, very often people will lose marks because I've just learned about solubility equilibrium, and so when I'm writing my net ionic equation, I'm going to write it like this. But you're still just doing double replacement reactions, so don't make that mistake, okay? If you're just asked, what is the reaction when these two things are mixed, you're writing a precipitation, and the solid goes on the right. Let's practice picking what kind of reaction we're going to use. And just so we're clear, you do not need to solve these questions. You don't have the tools in your toolkit to solve all these questions just yet. But let's say I asked you to write, we're just going to decide, do we want the precipitation equation or do we want the solubility equilibrium equation? Write the net ionic equation that occurs when equal volumes of 0.2 molar barium chloride and NH42SO4 are mixed. Tell your partner, do you think we will be using a precipitation equation or a solubility equilibrium equation? Shall we vote? The sign for P is a little bit tricky, okay? So what you do is you put your fingers, your two fingers like this. So your pointer finger goes up and your middle finger goes out a little bit, and then you put your thumb in between there. This would be the letter K, but if we turn it upside down, it's the letter P. Okay, so that's letter P. So P is a little bit difficult, but just remember your two fingers go like that, and then the thumb. And then S is much easier. S is just you make a fist, but you put your thumb in front of your fist. Okay, so are we going to be using a precipitation equation here or a solubility equilibrium equation? Yes, that is a precipitation equation. Yes. So let's just do a quick review of how we thought, how would we write this net ionic equation if we wanted to do it really quickly? Well, we have barium, we have chloride, we have ammonium, and we have sulfate. Barium sulfate, is that soluble or low solubility? Low solubility. Okay, so barium and sulfate are low solubility. How about our NH4 and our Cl? Those are soluble. So if we were to do our net ionic equation the quick way, what would we put as our product? Barium sulfate, BaSO4, and they're both 2 plus 2 minus, so there's no coefficients needed, and that's going to be our solid. And then all we need to do is put barium together with sulfate, and remember to put in our aqueuses, and we're done. We won't be solving them all, but I thought that one was a nice little easy one, so we'd do that. Next one, molar solubility of, I know you don't know what that is yet, but you don't need to, we're not solving for it. The molar solubility of lead iodide is 1.52 times 10 to the negative 3 molar. Calculate the value of KSP for lead iodide. Will we be using the precipitation equation or the solubility equilibrium? Yes, that's going to be our solubility equilibrium. The fact that it mentions a KSP in the question is a huge, huge clue that we will be using the solubility equilibrium. Why don't you practice writing the solubility equilibrium for lead iodide? Give it a go. Once you've written it, check with your partner, see if they got the same thing as you. Where do we write the solid? On the left. So we have PbI2. And all we do when we're writing a solubility equilibrium is we are writing the dissociation. So what does this dissociate into? This Pb2 plus and I minus, except for, oh, we have two I minuses. Both of those are aqueous. What kind of an arrow do we use? Equilibrium arrow. All right, the next one's a little, like the wording might be a little tricky, but you can do this. A student titrates a 10 milliliter sample of well water with 11.97 milliliters of 0.100 molar AgNO3 to precipitate the chloride ion in the well water. What is the concentration of chloride? Chat with your partner, decide what you think. We're going to vote on this one. Are we going to use a precipitation equation or a solubility equilibrium? Nobody's chatting with their partner except for like 2 people, maybe 3. All right, let's vote. You can also vote I for I don't know yet. Okay, so P, remember 4-finger up, 3rd finger pointing there, go like that and then turn it upside down. That's a P. S, thumb goes in front of your fist. 5, 4, 3, 2, vote. Okay, we got some P's, we got some S's, we got some I's. All right, let's talk about this one a little bit. Are we interested in the equilibrium that forms after we've had a precipitate forming? Or are we interested in the process of forming the precipitate? The process of forming the precipitate, because we're going to be wanting to know how does the Ag react with the Cl, which means that my Ag and my Cl are going to be my reactants, right? And I want to know, a titration is always, what ratio are they reacting in, right? Cl, one-way arrow or two-way arrow? One way, because I don't care what happens. I don't care if there's an equilibrium set up afterwards. I just care that they're reacting 1-to-1. And then maybe I have an indicator that tells me when the reaction is complete. Yes? AgCl, solid. Now, how did I know to ignore my nitrate there? Yes. Nitrate is soluble with everything. So even if I were to write out my ions like I did previously, right, I could say, okay, I've got an Ag, I've got an NO3, and I've got, oh, nothing's paired up with the chloride. I haven't been told anything. And quite frankly, it's because if you go and sample some water from a well, that's a natural source. Maybe the chloride is partnered up with some sodium in some cases. In other cases, maybe some magnesium, some calcium. There could be any number of different cations in a natural source of water. So we don't even know what sodium's really partnered up with. But if we're reacting these things, sodium nitrate is soluble with everything, and those leave us only with the silver and the chloride. Okay, so that's how we know that that's what must be reacting. Oh, and I must not forget aqueous, aqueous. Calculate the concentration of chromate ion in a saturated solution of calcium chromate. Chat with your partner, decide, do we want a precipitation equation or a solubility equilibrium? All right, we're going to vote either I don't know, precipitation, or solubility. 5, 4, 3, 2, go. Yeah, it's going to be a solubility equilibrium. The biggest clue is that I gave you a KSP here. However, another clue, if I didn't give you a KSP and let's say you had to look it up on a table, okay, so maybe I didn't give it to you, you could tell because it talks about a saturated solution, and we're going to talk about those later, but in saturated solutions, there is always an equilibrium. Okay, so saturated solution is a good clue that you'll use solubility equilibrium. And our equation would be CaCrO4 solid on our left in equilibrium with Cr2 plus Cr, oh, whoops, Ca2 plus, oopsie, plus CrO4 2 minus aqueous and aqueous. Back to our solubility product constant. Professor Dave talked about this, where the smaller the solubility product constant is, what can you say about how soluble it is? The smaller the KSP is, that means that these ion concentrations must be smaller. Yes? In order to have a smaller KSP, the ion concentrations have to be smaller, which means you weren't able to dissolve as much. So the smaller the KSP, the less soluble something is. You will even find things with KSP values minus 30, minus 50. Those are very, very insoluble. They would have only like 1 or 2 ions every once in a while sort of dissolving. How about you take a look on your page 5 of your data booklet and find the least soluble salt. Anyone think they found a contender? A salt's just an ionic compound. Yeah, you're right. All right, we have any contenders? Yes? Iron hydroxide, 2.6 times 10 to the negative 39. That sounds like an excellent choice. Okay, there's another one which is 10 to the negative 37, which is awfully close. And in fact, we can't really tell if it's copper sulfide or iron hydroxide because we can only use this compare KSP if the ratio between the ions is the same. And in this one, we have a 1-to-1 ratio between our ions. And in this other one, we have a 1-to-3 ratio between our ions. So we would have to do some fancier math to decide actually between those two. Okay? We're not going to worry about that fancy math yet. All we're going to worry about is that both of these are contenders for being the least soluble. Later on, we'll come back and we'll decide which one wins. Okay? But we'll wait on that one. It'll be a knockdown fight between those two. But if all salts have the same ion ratio, then you can use this method to directly compare their solubility. You don't have to do any math or anything. You just look at the KSP. Okay? This method, just look at KSP. And if we take a look at our salts here, they do all have the same ion ratio. Yes, we have a 2 silvers for every 1 carbonate, so that is our 2-to-1 ratio. We have 1 barium for every 2 fluorides, so that's a 1-to-2 ratio, and a 1-to-2 ratio is just as good as a 2-to-1 ratio. They work the same mathematically, okay? So 2-to-1 and 1-to-2 are the same for these purposes. And in our last one, we have a 1-to-2 ratio, and if that is the case, then we can just look at our KSPs. Taking a look at these, tell your partner which one is the most soluble. Which of these 3 salts is the most soluble? We're going to vote on this one. You either get to vote A, which is your thumb on the side of your fist, okay, and your fingers flat on your palm. A for AgCO3. B for barium fluoride. Or we just learned P. Okay, so P for PbOH2. 5, 4, 3, 2, vote. Yeah, B is the most soluble, barium fluoride. It has the largest KSP, therefore it is the most soluble. Who is the least soluble? Would that be A, B, or P? 5, 4, 3, 2, go. Yes, that would be our lead. So we have the smallest KSP is the least soluble. So if we were to order these, then we would say from greatest to smallest, we would say, does it say from greatest to smallest? From most to least soluble, so we'll go from most. Barium fluoride has a greater solubility than our one in the middle, which is the Ag2CO3, which is greater than the least soluble, which is PbOH2. Oh, and look, everything I wrote is already there, but that's okay. Well, you know, sometimes I'm like, do I write it down so that if you're away, you can like have it there, or do I just write it on the spot? I don't know. Anyway, let's just take a look, make sure that you know this only works for compounds with the same ion ratios. So, can we use it for these ones? 2 to 3, 2 to 3, 3 to 2. Are those ones okay? Yes, that's good. Can we use it for 1 to 1, 1 to 1, 1 to 1? Yes. Can we use it for a 1 to 1, a 1 to 2, and a 3 to 2? No. Okay, and we'll learn how to do that math, but not right now. Writing the KSP expressions. The biggest thing here is that there are 2 steps. Many students forget step 1 and lose a half a mark. You must write the dissociation equation or the equilibrium equation, okay? The solubility equilibrium equation. So if we're looking at calcium carbonate, you need to write that. Do not skip this step. And then I think I meant to write the KSP expression, but I didn't. So let's see if you can write the KSP expression. KSP would be equal to the concentration of who? Calcium times the concentration of carbonate. That's it. That's easy. Yeah? Just like KEQ, just with a new name. The only thing here, I mean, this is pretty straightforward. Don't forget, you must do both steps, right? 0.5, 0.5 equals 1 mark. Woo, okay? Don't do both, you only get a half a mark. I just want to check with you, what is wrong with this? Yes. I have a coefficient in my brackets. No coefficients in the brackets. It's been a while since I mentioned that, so I thought I might as well say it again. Make sure we don't have any coefficients in the brackets. I believe that might be it for this one. When is this class over? Friday, 1:53. Oh, okay. Well, we could get a little start on 3.1H. Little start. And the first little start will be to take that second un out of that, because otherwise we have unsaturated and unsaturated solutions. And that's a stupid title. So we're going to get rid of that second un. Okay, unsaturated and saturated solutions. That makes a lot more sense. Hopefully, the definition of an unsaturated solution is a review from grade 11. Okay? It is a solution that contains less than the maximum amount of dissolved solute. All right? If in an unsaturated solution, if undissolved solute is present, and this is where we get into grade 12 stuff, because we start talking about rates and forward reactions and reverse reactions. If there is undissolved solute present, if our solution is still unsaturated, we are not yet at equilibrium. Okay? the rate of dissolving will be greater than the rate of precipitation. Think about it this way. If we had a beaker and we threw some salt in and we stirred it, there is a process by which both of these are happening. Can you see all the little red arrows? That's all dissolving. But because we're in grade 12 now, we know that reactions don't always just go one way, they also go the other way. Sometimes a particle will join back up with the crystal, and that process is called recrystallization. Okay? But if we're going to be dissolving things, if we're going to go from a whole bunch of solid to a little bit of solid, the rate of dissolving has to be faster than the rate of recrystallization. Yes? In order to like actually get stuff to go into the... Well, that's annoying, but okay. Anyway, in order to get it to dissolve, the rate of dissolving is faster than the rate of recrystallization. Consider the following. If we put some solute into the solvent, at the moment you put it in, the rate of dissolving is high because we've got lots of solid, but the rate of precipitation is 0 because guess what? We don't have any undissolved ions yet. There's nothing there. So can we have a reverse reaction? Is it possible? No, because you can't have recrystallization if there's nothing to recrystallize. However, as time goes on, we actually do end up with some ions. And so as those ions concentrations increase, now our reverse reaction is starting to get faster. And it might be that we run out of solid. Yes? You know, if you take some sodium chloride and you sprinkle it into the water and you dissolve it, and it's all gone, you just ran out of solid. And at that point, if you run out of solid, all you've got is this. There's no solid. That is an unsaturated solution. Okay? Or, let's say you just kept adding extra solid and kept stirring. Yeah? Add some more solid, keep stirring. Eventually, you're going to have enough ion concentration that the rate of recrystallization is equal to the rate of dissolving. If the rate of the forward and the rate of the reverse are the same, what is true? We are at equilibrium. And the solution is it still unsaturated? It is saturated. No more can dissolve because every time one dissolves, another one recrystallizes. So you can't get any more to go in if the two rates are equal. Okay? So this is a saturated solution. And I think we have run out of time for today. I'm going to put your homework online. Okay? Basically, you're going to be studying for your quiz, doing the questions on that previous one we did, 3.1G. And I might give you a little bit of reading in Hebden as well. Okay, not a lot, just a little bit. If you don't have your Hebden at home, it is in our files on Teams. Okay?